In this lecture, I would like to discuss about the concept of resonance energy, examples of molecules showing resonance, concept of formal charge, and calculation of formal charge. So, what is resonance? In number of molecules, the resonance is present. The molecule cannot be represented by a single structure, but its characteristics properties can be described by two or more different structures. It means that molecule cannot be represented by a single structure. It can be represented by a number of structures, different structures. Then what is the true structure of that molecule? Therefore, it is said that the true structure of the molecule is said to be a resonance hybrid of these structures. When a molecule cannot be completely represented by a single structure, but its characteristics properties can be described by two or more different structures, then the true structure is said to be a resonance hybrid of these structures, and that possible structures are called resonating structures, and we can say that there is resonance between the various possible structures. Let us take the example to explain this. For example, water molecule. For example, hydrogen molecule. So hydrogen molecule can be represented in this way. This is the first structure of the hydrogen molecule. Then second structure should be like this, and third structure can be represented in this way. It means hydrogen molecule is having three possible structures. Hydrogen molecule cannot be described by one structure. It can be represented by number of different structures. So what is the true structure of the hydrogen molecule? The true structure is said to be a resonance hybrid of all these three structures. The true structure of the hydrogen molecule is the resonance hybrid of all these three structures. The structure first, it is a covalent structure, covalent bonding. Structure second and third represents the ionic. So the true structure of the hydrogen molecule, it is a mixture of all these three structures, that is resonance as well as that is covalent as well as ionic. So therefore we can define resonance. Resonance is the description of the electronic structure of a molecule. Resonance is the description of electronic structure of a molecule or ion, by means of which several electronic structures in which each structure contributes in the description. Resonance is the description of the electronic structures of a molecule or ion by means of several electronic structures in which each structure contribute in the description. So in these three structures now, the each structure is contributing in the description, and this is simple one, the electronic arrangement, electronic description, electronic structure of a molecule or ion. Let us say now in hydrogen molecule, suppose there are two electrons are present. Covalent bond is formed by the sharing of the electrons. Let us assume that the two electrons should be goes onto the one atom. So one atom, one of the hydrogen atom acquires negative charge and other acquires a positive charge. Similarly, the two electrons should be present onto this hydrogen atom. So it will acquire the negative charge and it will acquire the positive charge. So hydrogen molecule is having three possible electronic structures. But the true structure, it is the contribution of these all three structures. So it means that the hydrogen molecule is having the resonance. Hydrogen molecule, it is having the resonating structure, three structures. Now resonance can be represented by such arrow, two-side arrow. When we show the resonance, it is represented by the two-side arrow here. Mathematically, resonance is expressed as by saying that the wave function describing the molecule. Wave function describing the molecule psi c is the linear combination of wave function describing the molecules. Okay, so that is psi 1, psi 2, psi 3. So psi c, it is equal to, if the molecule is having three structures and in terms of the wave function, it should be represented as C1 into psi 1 plus C2 into psi 2 plus C3 into psi 3. So in case of hydrogen molecule, it is represented now in this way. For the hydrogen molecule, we can represent the equation for hydrogen molecule. It should be represented now in this way. So let us see here. So total psi, it is equal to, or psi c, it is equal to C1 into psi 1 plus C2 into psi 2 plus C3 into psi 3. Hydrogen molecule is having three structure. So it can be written in this way. Okay. So it means that in the hydrogen molecule, it is not described by only one structure, covalent bond, or by the pure ionic structure. It should have both covalent as well as ionic character. Hence, the true structure of the hydrogen molecule is considered as a resonance hybrid of the contributing structures. That is a resonance hybrid of the contributing structures involving both covalent and ionic bonding. So you can see here involving both, this is covalent bonding and this is ionic bonding. So the true structure of the hydrogen molecule is the resonance hybrid of these three structures, and it shows the covalent as well as ionic bonding. So this is the equation of the resonance. Psi c, it is equal to C1 into psi 1 plus C2 into psi 2 plus C3 into psi 3. Now due to the resonance, the energy of the molecule becomes lower than any of the resonating structure. Whenever there is a presence of the resonance in a molecule, then the energy of the molecule becomes lower than any of the resonating structure. Therefore, resonance gives extra stability to the molecule. The molecule, it is stabilized by the resonance. So those molecules who are having the resonating structures, that molecules are having the extra stability. Due to the resonance, the energy of the molecules becomes lower than any of the resonating structure. Therefore, resonance gives the extra stability to the molecule. Okay. Now, what is resonance energy? Resonance energy is the difference between the actual energy of the molecule. Resonance energy is the difference between the actual energy of the molecule and that of the most stable of the resonating structures. Okay. So resonance energy, it is the difference between the actual energy of the molecule and that of the most stable resonating structure. Now it is said that higher the resonance energy, greater is the stability of the molecule. So we can calculate here the resonance energy. It is equal to, whenever the molecule is having the resonance, it has the resonance energy. So resonance energy, it is equal to actual energy of the molecule minus energy of the most stable resonating structure. So in this way we can calculate the resonance energy. Now let us take the examples of molecules showing the resonance. So first example, it is carbon monoxide molecule. Carbon monoxide, CO molecule, carbonyl group. Now the carbon monoxide molecule is represented by these three structures. Let us see now. We know that carbon is having the valency 4. In the valence shell of the carbon atom, there are 4 electrons. So there is a double bond between the carbon and oxygen. Oxygen is having the 6 electrons. Let us represent this in this way. Carbon, it is having the 4 valence electrons. Okay. And oxygen is having the 6 valence electrons. In the valence shell of the oxygen atom, there are 6 valence electrons. So we can represent these 6 valence electrons in this way. Now the covalent bond, it is formed between these two. Okay, so this structure 1. Okay, double bond is there between the carbon and oxygen. Now these 2 electrons which are here onto the oxygen atom, that can be donated to the carbon atom. Okay, and there is a formation of the another bond in the second resonating structure. These 2 electrons, this is the structure 1 represented here also. Now these 2 electrons are donated to the carbon atom. So direction will be like this. So it means that on the carbon atom, negative charge is developed there, or accumulation of the 2 electrons will be here. And oxygen, as oxygen is giving the 2 electrons here, so it shows the positive charge here. 2 electrons are shifted towards the carbon. So accumulation of the 2 electrons here, carbon acquires the negative charge and oxygen acquires the positive charge. So this is the second structure. Resonance is the electronic description of the electronic structure of the molecule. So we just show the electronic arrangement in that molecule. Okay. So oxygen acquires the positive charge, carbon acquires the negative charge. See now in the third structure, third possibility, this double bond get breaks and these 2 electrons are shifted towards the oxygen. Electrons are shifted towards the oxygen. So what happens here? Oxygen will acquire a negative charge here, not positive. Oxygen acquires a negative charge here. And as the electron is shifting towards the oxygen atom, so carbon acquires the positive charge. Bond get breaks here and the electrons should be shifted here. So there is a positive charge onto the carbon. Okay. So let us see, this is the third resonating structure. Okay. So In this way, carbon monoxide can be represented by the three resonating structure, where one structure it is having the double bond, second structure it is having the triple bond, and third structure it is having the single bond. There is a single bond here, okay? Single bond here, and number of electrons, let us show this by this way, okay? This is the correct representation here. So this is the structure third. Now, what is the true structure of the carbon monoxide molecule? So it is the resonance hybrid of these three contributing structure. It is the resonance hybrid of these three contributing structures. Okay. And it is confirmed experimentally also. Okay. So you can see the calculated bond length of a double and triple bond between carbon and oxygen are 0.122 nanometer and 0.110 nanometer. Okay, double bond it is 0. It is 0.122 nanometer. This is this bond length. This is 0.110 nanometer. Okay, 110 nanometer. The carbon oxygen bond length determined by X-ray diffraction technique. Experimental bond length. This is calculated bond length, but experimental bond length it is 0.113 nanometer. Actually, triple bond length it is less, 0.110 nanometer. Double bond length it is 0.122 nanometer. But the X-ray diffraction technique shows the bond length between the carbon and oxygen atom is 0.113 nanometer. So it indicates that it is in between the double bond and triple bond. It means that in carbon monoxide molecule, not only there is a double bond, not only there is a triple bond, but it is in between the two. It is in between the two. This value is intermediate between the values of the double and triple bond, means this value. Okay, it is not only equal to the triple bond, but it is not equal to the double bond. It is in intermediate between this. Of course, it is near to the triple bond. Okay, so the experimental bond length determined by X-ray diffraction it is 0.113 nanometer, and that lies in between the double and triple bond. So this shows that in carbon monoxide molecule there is a presence of the resonance. Carbon monoxide molecule cannot be represented by one structure, it is having the number of the structure. So carbon monoxide is considered as a resonance hybrid above the resonance hybrid of the three structures. The experimental value 0.113 nanometer suggests that the bond between the carbon and oxygen is closer to triple bond. You can see here. It is closer to triple bond because this experimental bond length it is closer to triple bond. This 0.110, this is calculated, but experimental it is 0.113 nanometer. So it is closer to the triple bond. Hence, the structure second, it is the more possible structure for the carbon monoxide molecule. The structure second, it is more predominant structure. Okay. Similarly, the actual bond energy of 1057 kilojoule per mole has been found to be greater than the calculated bond energy. The calculated bond energy of the carbon monoxide molecule it is 726 kilojoule per mole. It means that there is a resonance is present. So the resonance energy of the carbon monoxide molecule is the difference between these two, actual bond energy and energy of the most stable contributing structure. So the difference it is 331 kilojoule per mole, indicates that in carbon monoxide molecule there is a presence of the resonance. So thus we represent here the carbon monoxide molecule is having the three possible structures, but the second structure it is more predominant because the experimental bond length it is near to this. So the true structure of the carbon monoxide molecule it is lies in between the three structure. That indicates that the carbon monoxide molecule is having the resonance. It is not described by the one structure, but it can be described by the number of the resonating structures. So this is about the carbon monoxide molecule. Let us take the another example, that is carbonate ion, CO3 2 minus, CO3 2 minus ion, carbonate ion. So let us represent here first carbonate ion in the electronic dot structure. Okay. First of all, represent the carbonate ion CO3 2 minus electronic dot structure. See here. Carbon it is having the valency 4. Okay. Oxygen it is having the valency 6. So let us represent the oxygen molecule here. Okay. 6 valency is there. Similarly, this oxygen atom valency is 6. Now this carbonate ion it is derived from suppose sodium carbonate. Sodium carbonate when dissociated gives two sodium ions and carbonate ion CO3 2 minus. So two electrons will be here extra. So one electron is here, extra electron. Okay, let us represent that extra electron by this way. And similarly here. Okay, two negative charges means two electrons are there. One electron should be onto this, one electron should be onto this. So it will acquire the negative charge, it will acquire the negative charge because extra electron is present there. 7 electrons now here. So you can similarly on this oxygen atom. Okay. So this oxygen atom is having the valency 6. 3 oxygen atoms are there. So we can represent as like of this. So there is a formation of the double bond here. This single bond here, single bond here. So that molecule can be represented by this way or by this way. Okay, carbonate ion. Now carbonate ion is a planar and its carbon atom is bonded to first two oxygen atoms by a single covalent bond. By a single covalent bond and one oxygen atom by a double bond. This means carbon oxygen bond should have different bond length. This is double bond and this is single bond. So it is having different bond lengths. But X-ray study shows that all the carbon oxygen bonds are of the same bond length. That is 0.131 nanometer. Okay, according to this structure, double bond, it is single bond. But X-ray study shows that all the bonds are equal and that bond length should be equal to 0.131 nanometer, which is intermediate between the calculated double bond length. This calculated double bond length, it is 0.12 nanometer and single bond length, it is 0.143 nanometer. 143 nanometer. So actual bond length, it is experimental bond length, it is intermediate between these two. It means that in a carbonate ion, not there is a single bond or not pure double bond is there. It is in between the single bond and double bond. Okay. So this is according to the resonance. It means that there is a presence of the resonance in the carbonate ion. Resonance is present there. Okay. So let us represent the resonating structure of the carbonate ion. So these are the three structures can be represented. You can see. Okay. This is the structure 1. Okay, two negative charges are there because of due to this oxygen is having extra electron, this is having extra electron. Now just shifting of the bond is there. Now double bond should be here, single bond here. So three possible way we can represent the carbonate ion. So carbonate ion is having the three resonating structure. It is not described by a single structure. It is represented by the three resonating structures. Okay, because the experimental bond length in the carbonate ion, it is 0.131 nanometer. The single bond length, it is 0.143 nanometer, and the double bond length, it is 0.12 nanometer. So it indicates that in carbonate ion there are resonating structures. Okay, so it is about the carbonate ion. Now let us see the nitric oxide molecule. So let us represent the electronic dot structure of the nitric oxide molecule. Nitric oxide. So you can see here, nitrogen is having the 5 valency. So represent here 5 electrons, two will be here, 2 will be here, and 1 will be here. Oxygen is having the 6 valency. So let us represent here 2 electrons here. Okay, 2 electrons here, and 2 electrons here. Now these there is a formation of the double bond in the nitric oxide molecule. So this is the one structure. You can see here that structure is represented, structure 1. Let us show now the electronic arrangement. Let us show the electronic arrangement. Okay, so one electron should be shifted towards the nitrogen. Suppose what happens, nitrogen is having now the extra electron, this, and negative charge will be developed there, and there is a shortage of the electron here, so it is having the positive charge. This is the second predominant structure. So it means nitric oxide molecule is having the two possible structure. We can show the arrangement of the electrons here. Okay, resonating structures of the nitric oxide molecule can be represented this. So both structure shows that it is an odd electronic molecule. Odd electronic molecule, but it is an odd electronic molecule. This odd electron will be here. Now here odd electron will be here. Okay, it is an odd electron molecule. The observed bond length of 0.104 nanometer is intermediate between the calculated double bond length of 0.115 nanometer and a single bond length of 0.10 nanometer. Okay, between the nitrogen and oxygen. It is assumed that the unpaired electron is spread over the whole molecule, and hence the molecule is represented with a double bond as well as 3 electron bond. Between nitrogen and oxygen, as shown in the structure 3. As shown in the structure 3. Once again, you have to see here. Nitric oxide molecule cannot be described by a single structure. It can be represented by a 3 structures now. So we can represent here. See, the third resonating structure now can be represented in this way. Nitrogen, oxygen, double bond is here. Okay, now these 2 electrons, see here, these 2 electrons and this 1 electron now here, it can be represented in this way. Let us see how it should be represented here. The third bond can be formed by this way. 1, 2, 3. Okay. See these 2 electrons of the uh, oxygen should be here and one electron should be here. Okay, so you can see here. So this is the possible third structure. Possible third structure can be represented in this way. Remember that when we represent the structure, the number of the electrons cannot be changed till these two electrons are remains on this. Okay, so this is the third possible structures, because you can see here it is a odd electron molecule. The observed bond length, it is 0.104 nanometer. It is in between the calculated bond length double bond length 0.115 nanometer and a single bond length 0.10 nanometer between the nitrogen and oxygen molecule. Okay, so it is assumed that the unpaired electron is spread over the whole molecule, and hence the molecule is represented with a double bond as well as a 3 electron bond between the nitrogen and oxygen as shown in the structure 3. Okay, so in this way we can explain here the resonance which present in the number of the molecule. We can take the another examples also to show the resonance. Okay, so what is the resonance? Resonance, it is the electronic description of the molecule. Resonance is the description of the molecule, description of the electronic structure of a molecule or ion by means of several electronic structures. One molecule can be represented by several electronic structures. Just it is an electronic arrangement. Okay, so and presence of resonance, it is confirmed by experimental results on the basis of X-ray diffraction technique. The bond length in the molecule can be calculated, and on that basis we can explain the concept of the resonance energy